In this video, we're going to extend our knowledge of classes by looking at Craig Reynolds' Boids algorithm. Craig Reynolds' Boids algorithm, like LinkedIn's ANT, is an algorithm that simulates natural systems of repulsion, attraction, and aligning in flocking systems. This is a way of simulating behavioral particles within a flocking organization. You can think of this like a flock of birds or a school of fish or any other kind of herding-based alignment system between multiple entities. So we can start by going ahead and taking a look at a description of this algorithm. Boids is an artificial life program developed by Craig Reynolds in 1986. So this is around the same kind of era as both LinkedIn's ANT and the development of cellular automata. Cellular automata being kind of primary to the other two, but both LinkedIn's ANT and Craig Reynolds' Boids algorithm being developed in the 80s. The Boids algorithm simulates the flocking behavior of birds and related group motion. And then they mentioned that his paper was published in the ACMA SIGGRAPH conference originally. The name Boid corresponds to a shortened version of birdoid object, which refers to a bird-like object. Reynolds' Boid model is one example of a larger general concept for which many other variations have been developed since. Now, if we go into the model details, we can see some rules that guide this particular algorithm. In this particular description, all they mention is the kind of rules for guidance or rules for coordination between elements in the system. So we're going to call these behavioral parameters. These behavioral parameters include separation, alignment, and cohesion. As it says here, all three of these feed into the kind of emergent behavior of the entire system. So each one of these has its own kind of responsibilities for certain patterns that we may recognize as an output of this algorithm. First, separation is the steering away to avoid crowding local flockmates. So any kind of neighbors in the area, neighboring agents or boids in the area, we want to steer away from. So if it's too crowded, steer away. Alignment is the steering towards the average heading of local flockmates. So what we want to do there is check where all of our neighbors are headed to, and we want to align with them so that we're not flying counter to the rest of the flock. And you can see the diagram here for that alignment vector. And then finally we have cohesion, which is steering to move towards the average position, center of mass of local flockmates. So in that case, we're going to move towards. This is just the inverse of the separation vector. So find all of our local flockmates, find an average point between all of them, and move towards that particular point. Another way of doing this would be to draw a vector to each one of these flockmates and then add all of those up, averaging them together by then dividing by the number of neighbors in your particular area. This is all going to be based on vector motion inside of Python. So the principle here is that we are a particle, or each agent or element is a particle within this system or a thing in this system. Call it a bird, fish, whatever you want to imagine it as, but it's an element in this system that responds to certain conditions around it in its neighbors. Each of those neighbors is also an element in the system. Already we're kind of getting this language out that each item or each instance exists within a kind of larger structure. So this is the kind of language of classes. So it already kind of makes sense. We have these properties and certain actions. Those properties and actions may be different for each of the agents or boids. And we have individual instances that have those kind of different properties or responses within a larger system. So this is going to be an optimal algorithm to write using Python classes. The extensions of this algorithm go far beyond just kind of simulating natural systems, where The most kind of applicable and exciting work being done currently is UAV or unmanned aerial vehicle swarm systems and aerial robotics. We can take a look at an example animation of what this kind of algorithm starts to appear like if we're just rendering each frame of the particle system. So you can see that when they get close together, they start to kind of move in these like herds. And then move further away, and as they get near each other, they start to align. So we can see the alignment happening, and then the kind of general avoidance and separation. So we have convergence, then alignment, and then separation eventually. There are many ways that we can weight each of these behavioral parameters within our script. We're going to go ahead and jump into Python and get started writing it, and then we'll discuss how we can adjust those parameters. Opening up a clean Python script, we can start by leaving a multi-line comment, introduction to classes, Craig Reynolds Boids algorithm for agent-based motion or flocking. Whatever you want to call it, however you want to conceptualize it or think about it, but the general idea is that we have a system that is coordinated with reactions or responses based on certain behavioral parameters. Now, what are the rules to this system? We have or we can call these, instead of rules, we can call these behaviors. What are the behaviors? We have a separation behavior. The separation behavior is going to steer agents away from neighboring agents. So I'm calling them agents, but again, we can call these anything that we want. Call them local flock mates, call them elements within a flock or a swarm. I'm going to call them agents. Then we have the alignment behavior, which will steer towards the average heading. Well, actually not steer towards, but adjust agents heading to match the average heading of local flock mates. That's a maybe more appropriate kind of description. So we're trying to align our direction and where we're heading with where everyone near us is also heading. Lastly, we have the cohesion behavior. What does the cohesion behavior do? It steers agent to move towards the average position or center of mass of local flock mates. And then I'm just going to leave a note for the actual kind of structure. So let's say agent structure. So what actually are these going to be in terms of Python representation? Well, I kind of mentioned this earlier, but this is going to be a vector-based motion where we take a point in space. So if I draw a point in Rhino, we want this point to be identified as one particular particle or agent in our system. And for each frame, we want to basically search within a radius to find agents within that specific radius to our current agent. So we currently just have 3 within this particular radius, our circle. So then we don't care about these other 2. So I can just delete those for now for this visualization. Now, inside of this radius, where we have our actual agent, we want to draw out a vector from our current position to each of these agents. If we add all of these vectors up, which we can visualize by just stacking them from end to end, and then drawing out, so drawing one summation vector. So from start to finish, that's the summation vector. If we scale this resultant vector by 1/3, since there are 3 agents that we are steering towards, or 3 particles that we are steering towards, we now get the resultant cohesion vector. So that first vector is representative of just the cohesion behavior, steering towards the center of mass of all of our neighbors within this radius. So that gives us one of our behaviors, which is going to be one input to our velocity or movement vector. So that helps us determine where we're heading. But that's just one, and we have three. What separation is going to do is basically this exact same operation, but instead of pointing towards, so instead of making an arrow towards these agents, it's going to flip away from them. Well, if we weight separation and cohesion exactly the same and input the same radius, then we would just cancel those out and we would get nothing. So what we want to do for separation and cohesion in particular is either weight one of these differently. So we could just scale down our separation or avoidance. And now if we add those vectors together, we get a much smaller vector heading towards our other agents, which is that size, but still in the direction of our neighboring agents. Alternatively, what we could do, instead of just making that a different size, is we could limit the radius that we're actually searching for our separation. So if we're checking only in this radius, we now have no particles that we want to separate from. What does this simulate? This simulates a longer distance that we can search for or search through to find neighboring agents that we want to be attracted to or cohere with. So think if you're a bird and your flock is far away, you want to get some feedback that tells you to go find the rest of your flock mates. So we want that cohesion radius to be really large at first, and then we want our separation radius to be quite small, because we want our separation to only be affected within a very particular area. So when our density gets too great, then we want our separation to kick in, and we then want to move away. So if these agents or this one agent got too close, then we would be able to move away. We would do that by drawing a vector to that agent. We could also weight it. So this basically gives us a vector pointed away from that particular point within our radius. And we could weight this to say, how about we make that twice as important? And we'll discuss how we do that in the script in a moment. But let's say that's twice as important. So we scale it up by 2, which is very similar to how we'll do it inside of Python. Now we have two vectors that are input into what we want to create as our one particular heading or one particular motion vector. Well, how do we add these together? What we do is we simply add them just together. So end to end, and then draw a line from our current point to the result of those two vectors stacked end to end. So now we're not going in either of these two, we're going in this third one. Now what is alignment then? Alignment says basically that every agent is going to have a particular heading or velocity vector. So if this one is heading over here, and this one is heading over here, and this one's heading over here, what we do is we take all of these add them all up, which gives us this one. And we average between this averaged vector and our current one, which we can't do this by stacking them end to end. Instead, we get something in the middle. So I guess we do calculate it still end to end, so it would be drawn out end to end, but then we would be dividing it by 2 to get the average. So scaled by half. And that gives us the average between those two vectors. So our resultant vector would be a heading at exactly this vector length. And we can adjust how each of those behavioral parameters impacts our resultant vector or our resultant velocity by weighting them using some multiplier. So what we're going to go ahead and do is we can actually leave these points, and I'll copy them as well so that we can just take a look at a larger grouping as we're going through this. So we'll use this as our points. And just while we're kind of here, let's just take a look at what the radius needs to be. So that's 13. So the larger ones are around 25 and the smaller ones there are 14. We could also type distance and check the distance between any set of points. So that's 25. So it looks like we could get all of the agents in our radius with 50 millimeters so that each one sees all of its neighbors. So we can start with a radius so that all of them see each other, but then we can start lowering it down so that our local neighborhood is smaller than our kind of entire, larger neighborhood here. So that's just something that's important to note. We want to start with our kind of flock. Our points are going to be our flock, so multiple points in Rhino. And then the second thing we want to know is generally what size, right? So my points have a spread of 50 millimeters, but your points might be in a different file unit. They might be a different size. We want to adjust all these parameters based on our kind of spread of agents in our file. So for me, that's a radius of 50. And that's also important in terms of how things actually move, or the kind of velocity vector, and how quickly our agents update in our space. So what is our agent structure? 3D points that represent each agent and can respond to neighbors or neighboring agents with or based on behavioral rules. Based on behavioral rules. What are those rules? Those are separation, alignment, and cohesion. What else do we know? Motion of agents is determined by averaged vectors to create a velocity. How do we get the next point? We can take our current position plus our velocity or our motion vector and add that vector to our current position, getting us the next position that we'll be in. So how to get the next position? Add velocity to current position, and that will give us the next position. So those are the general principles behind these kind of Boid systems or multi-agent systems or agent-based systems. And this is just a particular set of behavioral rules and parameters for this specific one, the Boids algorithm. So like anything inside of Rhino, we need to import Rhino script syntax as rs. So when we're using Python connected to Rhino, we need to be able to access our Rhino functions. Next, we need to read these points into our Python script. So right now they're just points, not agents. So rs.get objects. We have multiple, and we'll give ourselves a message saying select agent points, so that we can remember that they're points here that we need, and then a filter of rs.filter.point rather. Okay, now we can go ahead and copy this down, and we'll step into our next step. So this is just going to get us started, and now we're really going to jump into some of our programming structures. We have properties and we have specific actions that particular instances need to make. What structure best suits that? A class structure. So we'll call it class agent. You could call this class Boid. Just remember whatever you name it. as we'll have to refer back to it later. How do we use these points inside of our agent class? For now, let's just say pass. Well, we want a particular instance of the class agent. So we want to construct one instance of the class agent for every point that we have in Rhino. How do we do that? Well, we could pass all of our list in here, but that wouldn't give us each point. That would give us all the points. Instead, what we want to do is we want to loop through for point in points. And now we can create an instance by calling agent. And now we need to feed something into our agent in order to respond to this particular point that we are accessing. So we're going to consider the points we have in Rhino as the starting points in our agent. So that will be the starting point, and then we'll add all of the functions for the behavioral responses to create vector motion, and then we'll find ways of rendering and recording that so that we can visualize it. So for point and points, agent. Well, how do we pass something into an agent or a class structure? We create a constructor function. What do we need besides our constructor and our reference to self? We need the variable that we're going to pass in. What are we going to pass in? Not the point, which is the GUID, but we want the actual X, Y, and Z coordinates. How do we get X, Y, and Z coordinates? Using Rhino script rs.point coordinates of point. If we pass that into our constructor, we can pass it in as not as point, but as our position, because this is going to be our X, Y, and Z position. So underscore pause to pass it in. And now let's set this as a property of our class, self.pause equals underscore pause. Let's go ahead and print self.pause as well so that we can check and make sure that this is actually working. And one last thing that we want to do is just give ourselves a name. So we'll say my agent equals agent. Right now we're not going to do anything with that, but we know that it's best to store these instances in variables that we can refer to later. We'll take a look at how to augment this in a moment, but for now this will work to get us started. So if we click play, select all of our points, and then hit enter, we get a printout in our console of all of the point locations of our agents. And we see they're all on the XY plane, so the 0 Z value for every single one of these points. This is going to work totally in 3D, so feel free to just move any points up in space if you would like. Just for simplicity's sake, to visualize for this example, I'm going to keep them in the XY plane until the very end, but feel free to test however you want. One thing to note is that the kind of structure in your setup, meaning like the more structured or more kind of regular the setup is, the easier it is to debug whether or not your code is actually working. Meaning, if you have the 4 corner points of a square, you would be able to expect some degree of symmetry when you actually kind of run this script. So if there's not symmetry, then we can kind of debug what that issue might be. So just keep that in mind as we're going through building this out, that if you have a chaotic setup with the points, it might be harder to debug. Okay, so this is all working. Let's go ahead and copy this, comment it out, and then paste down below for our next step. What is our next step? Our next step is to do something with this point. What are we going to do? We're going to add a vector to our current position to update that position to move it in space. How can we do this? Well, we can do this first by storing a property, self.vec, and we can set this equal to some vector. So let's just say 0, 0, 1. So a vector, 1 unit in the z-axis. I'll remove this line between those. And then how can we use this vector? Well, we're going to make another function, and we're going to call this function move. This is going to be the function that actually performs the movement or applies the movement to each agent in our system. So def move, feed in self, and then what do we want to do in our move function? We want to update our current position. What do we want our current position to be equal to? Well, our original position plus our movement vector, which is self.vec. Now, if we want to run that function, how do we run a function? We call that particular instance, so my agent dot move. So in our looping through of all of the agents, we can say my agent dot move. Now, since we're not actually adding points in our document, if we hit play, we wouldn't be able to visualize that and see what's going on. So one last thing we're going to do is add a print statement of my agent. And what do we want to print here? We want to print the updated position after the move. So what we should see is that all these points that were on our XY plane with 0 z value, when we print their position, each one of our agent's position, so my agent dot pos gives us every single one of our constructed agents. So my agent dot pos, we should now see that their z value is 1 unit larger. So it is a value of 1. So if I click play, select our agent points, hit enter, we now see that all of those agent values are 1. So that's all working perfectly. Now, as we've seen in previous examples with class structures, especially when working with, let's say, the multiple ants in LinkedIn's ant, what we typically want to do is construct a list first of all of our agent instances. So create all of the instances of the class. And then if we have something like a move function, we actually want to take that out or strip that out and put it in its own for loop so that we don't iterate through each of these points only, but that we also go through not just one step as well, but we also go through multiple steps moving all of the agents together. Well, how do we do that? We can do that by separating this move call inside of its own loop for I in range 10. And now here we don't have my agent anymore. My agent is up here. So as we loop through for point in points and set my agent equal to that agent instance, we're only going to result in one agent called my agent at the end, which is the last one. Well, how do we fix this? Just like in LinkedIn's ant, when we use multiple, we need to append each of these instances to a larger list called population. In order to append to that list, we need an empty list. So we can set population equal to an empty list, open and close square brackets. Now we still don't have my agent here, and we've actually just removed the variable entirely, so we would get an error if we ran this. So what do we need to do inside of our loop? Well, we don't want to just loop for 10 steps. We also want for each of those steps to loop through for my agent in our entire list population. Now if we tab all of that in to align it, what are we doing? We're first instantiating all of our agents, storing them inside of a list, so every instance reference stored inside of a list. We're then looping through 10 times, so we're stepping in one time. In that first time, we're then saying for each agent, for my agent in population, call my agent.move. And then we're going to print each position. So what we should see in my agent.pos, this printout, is we should see however many points we have, so 24 points, we should see 24 points each step, so 10 steps, so 240 total printouts, where we're incrementing one unit in the z-axis each time. So if I click play, select our points, hit enter, we see that first it's printing out our positions with a value of 1, and then 2, then 3, then 4, then 5, then 6, then 7, and so on, all the way to 10. Now it's getting to 10 and not stopping at 9, and that's just because we're moving, so we actually start with a value of 1 and then go to 10 instead of 0 to 9. So we're just shifting that list, and that's because we're printing after our move function. Okay, let's go ahead and copy this down, comment it out, and jump into the next step. Well, what is our next step? Just like in previous examples with classes, we want to build a render function that can actually help us to identify what is happening so that we don't need to rely on just print statements. What could our render function be? First, I'm going to define it. So def render. What could our render function be in this case? Well, what if we just wanted to add the points to our document? So we could just visualize the points being added to our document every single time we move it. How would we do that? We use rs.addPoint. We've used that command before. So rs.addPoint, what does this take in? A point input, or x, y, and z value. What x, y, and z value do we want to give it? Our self.position. Now, if we just called it in our constructor, so call this function, self.render, in our constructor function, we would just render the initial position. So we don't want to do that. So let's look for a different spot. If we call it, well, we could call it after the move, I suppose, inside of the for loop. But if we know that we want to do this kind of rendering every single time we move, what indicates every time we move? The move function, right? So if we didn't want to separate it inside of our loop, and then we'd have to refer to it as my agent. If we didn't want to have those as separate calls outside, we could simply just say, update the position, and then add that point to our document. So calling self.render inside of our move function. So this call is going to run the function, update the position, call the render function, adding that updated position to our document. Now we can click play. I'll also delete that print statement actually. Now we can click play, select our points, and hit enter. And now we see all of our points updating in our Rhino space. So they're all incrementing 1 unit up in the z-axis, all 10 total times for each agent. And you could see even the stepping was happening, incrementing through each agent. So if we play this again, we see each agent move 1 step and then go up to the next one and move 1 step. And that's telling us how this looping is actually set up. So our nested loop here is iterating through all agents and then like updating each position, then going through all agents, then going through all agents, and so on, all the way through. There are ways that we can structure this like we did in our LinkedIn's ant, where we have a set of states or kind of temporary positions. In this example, we're not going to do that. Sometimes people will set up different functions, a move function and then a run function, or an update function and then a move or a run function, in order to first update all of the positions into a temporary list and then actually update the position. We're not going to focus on that in this particular video, but it is something that you could add if you wanted to kind of update the structure we're going to be using. So as we're talking through this, just keep that in mind. If we did have a symmetrical set out, you won't get symmetry because there's a certain order that our loops are stepping through. There is a solution. We're not covering it in this video. Okay, so we now have that visualizing for us. So now we can just go ahead and copy this and then comment it out and step into the next step. So what if instead of drawing points, which kind of become chaotic when we just see them as points, drawn out in space in our Rhino file, it can be hard to understand which point belongs to which agent, especially if they started kind of crisscrossing in space. So what's another way that we could actually render these so that we can see them visualized for us? Well, one way is we could just store a list of all of our positions. And then what do we do with a list of points that might be useful for us in Rhino? Well, we could draw a curve or a polyline, which takes in a list of points. Why would that benefit us? It would draw out the trail of all of the point positions where our agent has been. And then we get all of those connected in either a polyline or a curve so that we can see that drawn out in space, and we can understand their motion very easily from the start because they start all within a starting point at our agent's starting point, and then they move through space in a continuous curve or polyline. So if we wanted to make that update, the first thing we would need to do here where we're calling our render function, we can just go ahead and delete that. We're not going to need that right now. We'll come back to that and we'll place it somewhere else. So I'm going to delete that render function call. We're going to leave our render function because we're still going to use that. So what do we need? We need to store our points. So let's say store history of point locations. How do we do that? Well, we would need somewhere in our constructor a list of point locations or history. We can make this list by saying self dot, and we could just call this history, or since these are going to be the trails of each of the agents, we could also call this trail points, identifying it as a list of points, not the actual trail curve. So self.trailPoints equals, and then in open and close brackets to create that empty list. Now every time we move, we want to append to our trail points list. So self.trailPoints.append. What do we want to append? Our updated position. Now if we did this, it would omit the first position because we're only appending after we update. Well, how do we fix this? We can just add the first append inside of our constructor to get our initial position, and then append to get all of the rest of the positions. Now, if we wanted to wait until we've moved all of our agents, all of the times, all of the steps that we've done before drawing this actual curve out, then we would just want somewhere below here to say that self.render is what we had, but we can't refer to it as self outside of our agent class, right? Outside of our actual class. What do we need? We need a name. How can we get this name? We can say for my agent in population, not self.render, but my agent, to refer to that particular instance of my agent. Now, what do we want to do with this? When we call that render function, we want to step into our render function, not add a point to our document, but add, let's say, a polyline to our document. What do we take in here? We take in a list of points. What do we want that list of points to be? Our self.trail points, which is all of the history of points where our agent has been. So it's only rendering at the very end, which should be very quick for us. We're going to just iterate through all of the agents and draw out those curves so that we can identify their trails. Now if I click play, select our agents, it steps through drawing out those trails one at a time, going through each agent, because we're still stepping through each agent, but it's not stepping through each of the steps to render new polylines. So we only get one polyline or one trail curve per agent. Okay, so now that we have that visualizing, this will help us to kind of debug and make sure that whatever we're coding next, so the actual motion rules or behavioral rules of this agent, is following what we might expect. So this visualization and render function is going to be crucial so that we can actually see as we're building up our code how this operates. So I'm going to go ahead and copy and then comment out, paste below, and we can build our next set of functions. Well, what are our next set of functions? These are going to be our actual behavioral rules. For each of these behavioral rules, we can define a separate function, which we can call def seek, which is going to be our actual seek action. So def seek, what do we need as an input? We'll just feed in self, and then we'll leave a comment here and say for each neighbor, apply cohesion behavior add self.vec to steer towards each other, or each element, or each neighbor. Okay, and then we'll just pass. What do we need next? Def of void. So for each neighbor as well, apply separation behavior. And then here we can say subtract self.vec to steer away from each. And let's not call these self.vec actually, let's just call them the cohesion vec. And then let's say here we can have add separation vec, so vector. And we'll know that those two are going to be inverse unless we adjust that radius, but we'll just keep that in the back of our minds for now. And then we'll figure out how we can actually add those up in a way that works within this system. Okay, what's next? Our alignment. Inside of alignment, what do we have? For each neighbor, match alignment vector to current heading vector. And then we can pass. Now, in order to use these functions, where do we want to place the call? Well, everything we do based on the movement or to define movement of our particular agent is going to happen in this move function. If we place the call to all of these behavioral parameters after we've already updated our position, so if we said self.seek after our self.pause, none of our behaviors would matter because we're only updating our position prior to actually calculating the behavioral motion. So then what we need to do is we need to say self.seek self.avoid and then self.align. So we need to call all three of those functions, which right now we're just passing through, but call all three of those functions before we actually update our position. Now we're kind of giving ourselves a hint here that these three need to have something to do with an update to our self.vec if we want our position to change relative to these behavioral rules. So right now we're just going to leave them empty, but we'll keep that in mind. Now what else do we need here? Well, each one of these functions is asking for each neighbor within our neighbors list, so within the neighbors of a given radius. So then what do we need? We need a way of getting the neighbors closest to us. So getting in the neighbors list within a radius. So let's draw out a circle here of a given radius. So let's say a radius 10. So if we had a radius 10, then this particular neighbor, or this particular agent rather, would be cohering or seeking those two neighbors. And we would do this same action for all of the agents in our agent system. Okay, so then we need a radius and we need a function to be able to get our neighbors. What can we call that function? We can just call this function get neighbors, and we'll put this after the render but before the seek, avoid, and align. So we'll make a new function and we'll call this get neighbors. What do we need for all functions in a class? We need to feed in self. Inside of this neighbors function, we need an empty list to store all of our neighbors. Now, what do we want this function to actually do? We basically are checking whether of all of the agents we have in our system, which ones are close enough or closer than the radius of this circle, so within the distance of the radius of that circle. How do we do this? Well, first, we need to loop through all of our agents. So for other agent in, and then we can still use population here. So for other agent and population, we need to do a check of the distance for each of these agents, but not only do we need to do that, our population actually contains this agent itself. So if we want to exclude this agent, we need some input value, some identifier within, or some property you might say, within this agent that tells us which agent this is, so that when we do this check of our neighbors, we can say, we want to find the closest agent that is not this agent, right? So the agents within this radius that are not my current agent. How would we do that? Well, we could say here for I or for index, comma, other agent, and then we could use enumerate. So if we use an enumerate to unpack this list into both the index values and the actual agents in that list, or agent instances in that list, then we can use that index value to check whether or not our current agent is that index. But right now we have no way of storing that. So what do we need? We need a property called self.index. What does this equal? This will equal a variable which we'll pass in, which is going to be our index value. We're going to pass in a new variable called index into our constructor function. Where do we do that? We do it where we instantiate the agent instances. So right now we're just passing in our point coordinates. What do we want to pass in here? Well, we want to pass in our index value. Let's call it I. Right now we're just looping through for point in points. So we need to adjust this and say for I point in enumerate points, which unpacks our entire points list into indices and points. So we're now giving an index value saying this is the particular index for that agent. We're storing that as a property here. And now we can use this inside of our getNeighbors function by saying if index, so if the index of our neighbor is not equal to self.index, so if the index of our neighbor is not the same index as ourselves, that means it's a different agent, so it's not us. Then, so if rs.distance of that other agent, and we don't want the instance of the agent, we want its position property. So the distance from that point, we can see our distance function measures the distance between 2 points, so we need to feed in 2 point positions. So other agent.pos, and then what else do we need? Where are we measuring from? Our self.pos. What does this conditional need to say? If the distance is less than our circle radius. So if that distance is less than some variable radius. What do we want to do if that distance is less than our radius variable, which we also still have to define? We want to store that particular instance, so that particular agent, in our neighbors list. So before we move forward, let's just go ahead and declare that variable radius. Let's make that a global variable at the top. So radius up at the top of our script here is going to be equal to 10. I mentioned that 50 would catch all of the agents. So let's just start with 10 as I've drawn out a circle with radius 10 here. So we can start with a radius of 10. We can increase that to 50 to see how that impacts our behaviors when we step through. Now we have one last thing that we need from this getNeighbors function. We need to be able to store these neighbors or output the neighbors that we've collected in this list. Since we're not storing those in a list in our constructor within each agent, we need to actually pass this out as neighbors. So we need to say return from this function our list of neighbors. Now, where do we call this function? Well, we know that we need it in all 3 of our seek, avoid, and align scripts. So where might we call this? Let's call this before those 3 function calls. So we first get our neighbors, and then we're eventually going to use that information inside of our function calls. So if we're returning our neighbors list as well, then we need to store this in order to be able to actually use it inside of our move function. And we're going to store that in a list called neighbors. So neighbors equals the output of self.neighbors, which is our neighbors list. So this is how we're going to get all of the neighbors in our agent system within a given radius. So now we can click play just to check and make sure that all of this is running, although our seek, avoid, and align are not doing anything yet. So we should just see them incrementing in the z-axis still. So we can hit play, select our points, and they just increment and make lines in the z-axis. So straight lines pointed up. Now we can go ahead and copy all of this down and step into the next step. So comment these out and then step into the next step. What is the next step? The next step is actually building out our behavioral rules. So as we're building these behavioral rules, what do we need for each one of these? We need to loop through each neighbor in our list of neighbors. How can we do that? Well, we can pass in our list of neighbors here. So neighbors passed in, neighbors passed in, and neighbors passed in. How do we read them into each of those functions? We read them inside of our function definitions. So we can pass them in next to self, and I'm passing them in as an underscore neighbor so that we can read them in as underscore neighbors inside of the function. Now we only want to do these actions if we actually have neighbors. So we're going to add a conditional and say if the length of our list neighbors is greater than 0. So if it exists and is greater than 0, which we can just shorten to if length neighbors, then run each of those functions. Now what's next? We need to step into each of these functions and actually build their behaviors. So the first one we want to do is calculate our seek action. Well, how do we calculate our seek action? We can start by just reading our rule here. So loop through each neighbor. Okay, so for neighbor, or let's call it just for n, in, let's actually stick with neighbor. So for neighbor in underscore neighbors, looping through each neighbor in our list of neighbors. What do we want to do with each neighbor? Well, we want to find their position and we want to steer towards it. So we basically want to update our self.vec. So plus equals update our current vec by adding to it. What do we want to add to it? We want to add to it a vector which is from our current position to that neighbor. So what do we see here in our vector create? We see a to point and then a from point. So we want to go to this particular neighbor, so neighbor, and we can't just use the agent instance neighbor. We need to use neighbor.pos. Where is this from? This is from self.pos. And if we just add all of those up, our velocity vector is going to get incredibly high as we keep incrementing. So what do we need to do to adjust that? Well, we need to average all of these vectors. So not just add all of them up. As I showed in the kind of diagram as we were looking through, you add vectors to get a resultant vector by taking them and placing them on each other's ends, and then drawing the summation vector. So then we can draw out this vector, but to average, we need to then divide or scale by however many vectors we have. So scale, in this case, by 4, divide by 4. How do we do that inside of Python? Well, we can simply just say self.vec equals self.vec over length underscore neighbors. Now, before we get into our avoid and align functions, I want to take a look at a particular issue that we might have here. So when we only have one function and we're overriding the self.vec value, this is going to work. But if we override that self.vec value for the avoid and align functions as well, and update our behaviors or update our self.vec for all of these, then we're going to have an issue. So I'll just check and make sure this is doing what we're expecting and we're getting some type of cohesion behavior. But then I'll warn us that this is eventually going to cause an issue, which is because we're directly overriding our self.vec variable. So we're overriding our velocity, and we would do that in each one of these functions. So we want to be careful about that. So what I'm going to do is just leave that here, and we can just test and double check that this is actually running and that we get some type of cohesion behavior. So select all of our points. And now we get all of our points converging. So we see all of these points converging based on their radius. Okay, so that is in fact working, but it is going to cause an issue because we're overriding that vec value. So I'm now going to copy all of these lines, comment this out, and then let's jump into fixing that issue with our self.vec update. So the structure in general is almost there, but if we can't update our self.vec, what else could we do? Well, we could create a vector inside of this function, and we could just call this vector our acceleration. This acceleration vector is going to allow us to add the resultant acceleration vector or resultant vector to our current velocity to accelerate it. So think you're heading in a car at a constant speed. If you add acceleration, you start speeding up. If you add acceleration in a particular direction, then you start heading in that direction. So that's how we're going to use this acceleration vector, which is going to start at 0, 0, 0. So acceleration equals 0, 0, 0. Now just inside of this function, so we can take that acceleration equals 0, 0, 0, and we can now override anywhere that we have self.vec. So ACC plus equals that vector that we've created, and then ACC, and then ACC divided by the length of neighbors. Now, since we've made a local variable that is not a property of our class, if we want to use this, we need to return this. So we can return ACC. Now that we have a return, we need to output this where we're calling that function. So I'm going to call this seek acceleration or seek ACC. So now we can go through and do this for each of our behavioral functions. So we'll step into avoid. And just like with seek, we can start by making an ACC or an acceleration vector equal to a 0, 0, 0 vector. Then we need to increment through or step through each neighbor in our list of neighbors. What do we need to do here? So this is avoid, so we need to say ACC plus equals. And now we don't want the vector from our current position to our neighbor. We want the vector that is inverting that. So we can just copy this same thing, paste it down here. So copy our seek. How would we invert this? We want the vector from our neighbor position to our current position, which gives us the inverted vector, which would move away. Now, how do we average this? ACC equals ACC divided by the length of underscore neighbors. We could also shorten that to just be ACC divided equals ACC divided equals length of neighbors. Then finally, we just need to return this ACC value, and now we can store that in a variable called avoid underscore ACC and set that equal to that call to our function. Lastly, we need to do this same exact thing with a line. So just like the other two, we can say ACC equals, and then we can make a 0, 0, 0 vector, delete this pass, step through our neighbors for neighbor in underscore neighbors, ACC plus equals. Now, we don't want the vector from our current position to this neighbor. What do we want instead? We want to get an averaged vector of all of our neighbors' vectors. So we want to see all of their headings, average those, and allow that averaged vector to influence our current vector. So ACC plus equals neighbor. What property of neighbor? Neighbor.vec. How do we get the average here? ACC divided equals length of underscore neighbors. And then return ACC. And now where we've called that function, again, we need to make a variable, set that equal to that return ACC, which gets passed into our variable align ACC. We now have 3 separate ACC values. How do we get those into our self.vec? How do we get those into self.vec? We can say self.vec plus equals, and then here we can say total ACC. So that's going to be the summation or average of all of these acceleration vectors. How do we get that average vector? The same way that we've done the others, by adding them all together. So seek ACC plus avoid ACC plus align ACC. What do we need to do then? Divide by the length. And in this case, we don't need a length function or a length method. We just say divide by 3 because we know we always have 3 behaviors. So that gives us that averaged acceleration vector. And now if we have that total ACC, we add that to our velocity or our current vector. And then we're still adding that vector to our current position so that we can update our position based on that updated velocity vector. Now, before we actually test this, if you would like to test it, go for it. You're going to see some strange behavior that you might not expect. Now, why would we see strange behavior that we wouldn't expect? If you remember when I was talking about the seek or cohesion and separation, so seek and avoid or cohesion and separation behaviors, I was saying that we need, in order for those to actually work, we need different radii being sent in to each of these behaviors or each of these behavioral action responses, or else they just cancel each other out. So right now, our seek and avoid are entirely canceling each other out. So what would happen? We would just get points in our document that are aligning. Well, how are they aligning? Well, they're already going in the same direction. So we would see them just make straight lines. Now, how do we fix this? Well, we could fix this by variably weighting them using some behavioral parameter, let's say, that is a weight for each one of these behaviors. So how might we do this? Well, first, if we know that we have these variable weights and they're parameters inside of the class, so they're properties of the class, let's just go ahead and make those at the top here. So what can we call these? We can call these the name of those behaviors, and we'll set these equal to 1.0. So self.cohesion equals 1.0, self.avoidance or separation, let's say separation equals 1.0, and self.alignment equals 1.0. So they're all equally weighted here. And now we need some way of reading all of these values. I'll actually also shorten these to just co, sep, and ollie. And now we'll refer to each one of those three values. How can we variably weight each one of these? We basically want to variably weight them when we calculate them here in our average. So variable averaging or weighted averaging. Well, we could do that in this equation here, but that's maybe already a little bit messy. So another way of doing it is just when we return our acceleration, we could just say times self.co, our cohesion parameter, times self.sep, and then what do we say here? Times self.ollie. So now we get each one of those variably weighted relative to their behavioral parameter. So all we have to do now is change these behavioral parameters. If we don't change them and hit play, we'll just get straight lines still. So if I hit play, select our points, we get straight lines. Now we get much faster straight lines, and what you can see is happening here is actually our lines here are accelerating forward because our alignment is not taking our current velocity and averaging it with our neighboring ones. It's just steering it to get more aligned with our neighbors. So what we're seeing is still vertical lines straight up, but the velocity is actually changing, so it is variable. Now what if we don't care about our separation and we don't care about our alignment, so we want to turn those off and we just want to see coherence? How would we do that? We can just set the multipliers equal to 0 in both separation and alignment, hit play, select our points, hit enter, and now all of our points are seeking all of the averages. Now they're seeking them by a lot, so they're actually overshooting the points. So they're trying to cohere, and if we maybe gave them more time to cohere by stepping through a much longer range, so let's say 100, and then select our points, it looks like they're still too powerful, so they're actually stepping across and overshooting that cohesion. So what could we do with this cohesion to stop each of these agents from overshooting each other? One thing that we can do is we can, instead of just adding our total acceleration to our vector, is that we can average, so plus equals, or self.vec equals self.vec plus total vec, and then we can divide this by 2. So get the average of our added vec to our current vec. This will allow us to start steering instead of kind of overshooting those coherence points. So now if I click play, select all of our points, hit enter. So we're now getting them just barely moving in space. If we increase, that's because our coherence is 0 here. So 0.1, hit play, select all of our points, enter. Now we actually see our agents cohering, and they're snapping pretty immediately to cohere together. If we change this to 0.01, then we'll get an even more gradual coherence. If we increase this, we can see the velocity at which they cohere increases, and now they're cohering along a certain point. Now, what if we increase our alignment? So what if we say alignment equals 2.0? What we'll see is as the agents get within radius, they'll not just cohere along a specific point or at a specific point, but they'll also start to steer in the same direction. So if I hit play, select all of our points, hit enter, we see that it's much more gradual and we get alignment between all of our agents here. Now if we increase separation, we'll just get a delay in that same action. So the same action is being performed, but you can see that they're a little bit delayed, and that's just because that separation keeps them away from one another. So now we can go ahead and copy all of these lines, comment them out, and then we'll step into the next step. What is the next and final step here? Because we're already seeing agent actions being performed. What is the next and final step? The next step is to be able to input a variable radius into each one of the behavioral functions. Well, how do we do that? Right now we're calling our getNeighbors inside of our move function, and then feeding in our neighbors list, which is the same neighbors list, to each one of those behavioral functions. How else could we do this? Well, we could just go ahead and call that getNeighbors list not from our move function. So we can now tab those out. Not from our move function, but from inside of each one of our behavioral functions. So we now no longer need to pass in our neighbors, but inside of this function, we can first make that ACC vector and then say underscore neighbors equals self.getNeighbors. We can now delete this input into each one of those functions. So each of our 3 behavioral functions, delete that input. We're now running that getNeighbors function inside of our seek. And let's start out with just seek. So what do we need inside of here? Well, if we want to pass a unique radius here, we can do that by, instead of setting radius inside of our getNeighbors, we can pass in the radius value here, where we could now set a multiplier. So we could say radius times 2. And then in our other functions, we could say radius divided by 2, or radius divided by 4, or 8, or whatever we might do. So this will give us a unique radius to each one of these behavioral parameters. So neighbors equals self.getNeighbors, and then input that radius value. If we're inputting a value, we need to update that in our getNeighbors function. Well, how can we do that? We can just add a variable here called underscore radius, change that radius inside of the function to underscore radius, and that allows us to pass in this radius value. So we're still going to base it on that global radius, but we can use multipliers of it to get particular radii for each one of these functions. Now if I just copy this line to each one of our other functions, so align and avoid, or separation and alignment, well, for avoidance, I'm going to divide by 4 because we only want to avoid at the last moment. So we want to cohere under almost all conditions and only avoid at the last moment. How about alignment? Let's align with only our local flock, so let's just make that radius. Now, since we were checking for whether or not we have neighbors in our move function before, we now need to perform those checks since we're calling the getNeighbors function inside of our behavioral functions. So we need to say if length underscore neighbors. So if we have neighbors, then update our ACC. And we're going to just set that conditional for each one of these functions. So if length neighbors, then update our ACC. Otherwise, just leave ACC at 0. And we can do that here again. So if length neighbors, then update our ACC, and then return our ACC. So no matter what, we'll return our ACC, which will either be 0 or an updated value based on our neighbors. Now we can click play, select all of our points, hit enter, and we get all of our points cohering. Now we can adjust our behavioral values here. So we have them at 1, 2, and 0.2. So we could adjust these to make maybe alignment is 1.2, and then separation we can make 0.6, and then we can try and hit play again. Okay, so we might need that alignment value to actually be relatively high, so let's say 1.8, and then our separation we can say is 0.4 to just separate slightly once we get within that radius. But also, since we're now we have a big enough radius that we're actually basically reading in all of our points and all of the points are cohering together, what we might want to do is not use a multiplier on our cohesion at all. So we'll just keep that seek radius just as our radius. And then our avoid, we'll say, is our radius divided by 10. So only avoid at the very last moment. And then our alignment is going to be radius divided by 4. So we'll allow them to just seek each other and then align at a quarter of that distance. So now if I click play, select all of our points and hit enter. So now we get a lot more local behavior happening here with alignment just happening towards the end. And if we decrease our alignment value, so 0.1, separation as well, 0.1, and hit play, select, we get much more convergence. If we just increase our alignment, so 2.0, hit play, select all of our points, hit enter, we get a lot more alignment. So basically alignment is just kind of more parallel trails, which we start to see there. We could also decrease our cohesion to 0.1 to match our separation so that it's just alignment, which will now make it 1.0. Select all of our points. So we're just getting alignment with a little bit of cohesion here. So we can see we have an even more localized cohesion setup. Now, what if I started moving a few of these up in our z-axis? What would happen now? Well, it's still going to perform exactly the same, but it will just include more motion or more convergence in that three-dimensional space. So we're now just getting convergence on these specific points because the other ones are now out of the given radius. If we wanted to include them, we could increase this radius, so from 10 to 20. And now we should get more global convergence, which we see there. If we decrease that again, hit play, we now get more local convergence with that alignment happening as they come together. We could also increase our separation so that as they get so tightly bundled, we can actually repel them. So we see some jittering happening because they're trying to be repelled, but the alignment is also snapping them back into position. So maybe we make that 0.4, cohesion 0.2, and then alignment can be 0.8. Now if I hit play, select all of our points and hit enter, we get a healthy amount of alignment. And then once they actually collide, we eventually get them being repulsed by one another, creating these kind of dead ends. You can see here even the alignment is so strong that as they actually touch, one turns around to meet its other agent. What else could we do? Well, we could keep our convergence and our alignment radius the same. And then if we keep those values the same, then we would be averaging between the convergence and the alignment, and then we'll turn down separation, hit play, select all of them. So now we just get that nice clean convergence. If we decrease our coherence or convergence, then to 0.4 and then keep our alignment at 0.8, hit play, we should see a less kind of tightly wound bundle there. So we do see that less tightly wound bundle. So maybe a value of 6. So 0.6, 0.2, and 0.8 I think work for me with a radius of 12. That seems to be a good mix for this particular version of these agents. Now we have 3D agents moving in space, and we're storing or rendering their actions through a series of output trails. So that's all for this particular portion of the video. And in the second part of this video, what we're going to do is an adaptation of this script to actually snap, not just to kind of operate in space arbitrarily, so move through space arbitrarily, but to snap to an existing geometry, which in the example we'll use as a mesh. So sometimes these are referred to as mesh crawlers if you're using the actual mesh edges to kind of crawl on with these agents. But we're going to be doing something a little bit kind of beyond what a typical mesh crawler is. It's essentially just a three-dimensional agent that is just going to be snapped to the surface of a mesh. And then I'll show how to kind of process alignment to the mesh edges as well. So this is it for the three-dimensional agent structure. You can get a lot out of this, but what I'm showing next is really more for drawing on the surface of a geometry or kind of accenting edges, creating maybe a texture eventually. So you could use this in digital fabrication methods to kind of robotically mill based on these toolpaths, or to 3D print on an existing surface, or to draw on an existing surface. Really the kind of applications are quite wide-ranging. So I'm going to be showing that in the second part of this video. So starting with where we left off in the first portion of this video, I'm just going to select all of these lines of code that are uncommented at the end, open up a new Python file, and paste them in here. So this is our 3D agent, and I'm just going to leave a note saying 3D agents snapping or crawling on mesh. So the first thing that we're going to do is just simply take the points of motion and before updating them, align them to a mesh or snap them onto a mesh. So that's a quite simple operation that can quickly change the types of outcomes or the kind of operations or applications that you can do with these agents. Now the second thing that we're going to do is a little bit more complicated, but it's just one simple function, which is going to look at aligning these agent behaviors to the properties of a mesh. So I'll be a little bit more complicated, and I'll just show one example. There's many ways that we can do it, but it increases our range of application by a lot. So to start out, I'm going to delete the points that we had in our prior example. And we could just go ahead and make any geometry. But the key thing here is that we want it to be a mesh. So we could make a mesh sphere and run this on a mesh sphere. We could make some Boolean object and then remesh it. In the example, I'm going to show exactly that, which is a Boolean object that's been remeshed using quad remesh. So if you're not familiar, if we draw out a box inside of Rhino, we move that box somehow, Boolean these together. This is just one particular instance of this operation. So Boolean these together. And if we want the mesh of these, well, we could just type mesh, hit OK. And what does it give us? It gives us a polygonal mesh, which is exactly that geometry. The issue with using this mesh in particular, for the first part, this would be perfectly fine to do. We could also just use the poly surfaces, because you can do this first part with either a surface or a mesh, it doesn't matter. But with the second part, we want enough density on our mesh to be able to register the what are called the topology edges of the mesh. So we want to actually align our agent motion with the kind of direction embedded into the mesh. Now this type of irregular mesh does not give us that. So what do we want? We want a more regularized mesh. How can we do that? Well, we can use a command called quad remesh. Now if we hit enter, delete that initial box, what do we get here? We now get quad mesh that approximates that box. So we have nice clean transitions. which is great for this type of motion analysis. And we could even, if we didn't care so much about the particulars of the geometry, we could make sure all of these vertices are welded. So select all of those vertices. So those are all welded. And then we could go ahead and type smooth with it selected. And we could start to smooth out these two boxes. So I just ran that twice. So we get nice smooth boxes. So maybe I'll just use this for this particular example, although I have a different example in the project files for all of you to look at if you have access to those project files. So I'll just use this example. This will be our base mesh. Now, instead of drawing random points in space, what are we going to do? We're going to draw points on this exact mesh. So we need our vertex OSnap selected, and then we can just click to deposit certain vertices around our mesh. So those will be our vertex-based agents or point-based agents, and then we have our mesh. So the first thing that we need to do to adjust this script is we are going to need to update this self.pos to be not the pos, so not just a position in space. If we use this right now, hit play, select these points in space, hit enter, and then just for a moment, hide that box, we don't get them drawn out on the box at all. So if we want them drawn out on our box, so each of those polylines to be drawn on our box, then we want all of these subsequent points, so all of these updated positions, to be on the face of the mesh or on one of the faces of the mesh. How do we do this? We're going to do this by calling a function after we update the self.pos to again update that self.pos, and we can call this function snap to mesh to underscore mesh. So snap underscore to underscore mesh. Self.snap to mesh. Now we need to make this function, and we can put this above our get neighbors under our render function, and we can make this by saying def snap to mesh open parentheses input self and hit colon and enter. Now we're inside the tab space of this function. What does this function need? Well, we need a new point to give to update our self.position. What do we need to take in? We need to take in our current position. What do we want that point to that we're returning to be? Well, we want the returned point, so we know that we have a return point. We want that to be the closest point on our mesh. If we type rs mesh, and then as soon as we start typing closest point, for closest point on mesh, mesh closest point comes up. So mesh closest point, open parentheses, what does this take in? It takes in a mesh ID and a point. So we'll make a global variable mesh ID, which we need to set by getting that object in our Rhino document. So mesh ID, and then what is the point that we want to use? Self.pos. And it's important that our call to this function happens after we've updated self.pos, because we want the next point that is updated not to be off in space, but to be, we want to first calculate it off in space and then snap it back to our mesh. So we need to run this after we've updated it, which we are calling it after we've updated our self.pos. So that's an updated self.pos. And that will give us, what does it say it returns? A tuple, which is kind of like a list, but it's a nesting of two elements, in this case 2. So point and number. What is the number? The index of the mesh face. Okay, so what we'll do is we'll unpack that output into those two values. So anytime a return gives you multiple values, you can just set them equal to multiple variables directly. So we do that by just saying pt. So point is going to take care of that first one, passing that point into the variable pt, and then we can just say comma, and what is that next thing called? Index. So pt comma index equals rs.mesh closest point mesh id self.pos, and then we return the closest point. That's going to update our self.pos to the closest point on the mesh. And now all we need is our mesh ID. What is our mesh ID? Well, it's equal to get object select mesh or maybe we'll say base mesh. And then we need a filter, so rs.filter.mesh. Now when we click play, since we're already calling that, we can click play, select our mesh, select our agent points, and we see those same actions moving across our mesh. So our polyline is not mapping directly to our mesh, but that's just because our points are, and when we don't have a high enough density of points, we're getting those kind of runs across or kind of breaks on the surface of our mesh. So already we've gotten this to work, and that same kind of motion behaviors are now being updated by snapping to the mesh, which is affecting the overall pattern here. So if we take a look again, we can see that that motion, although still relatively similar, is starting to be adjusted slightly based on the kind of topology of that mesh surface. So we're getting kind of motion around the edges or towards the edges because it's snapping to those edges. So it is just a kind of brute force way of doing it, but it is also affecting the agent proximity relative to the surface of the mesh because we're snapping to it. So they're no longer floating around in 3D space. But it pretty much is still just calculating in 3D, and it's not actually taking into account how we would want to move on the surface of the mesh. What do I mean by that? Well, if we wanted a polyline drawn out on the surface of our mesh, we might want it to just follow these edges. Right? So if I just click continuously on these vertices and then follow those edges, we get a nice clean line drawn out following the topology edges of our mesh. How do we do this? We do it just like we did with the seek by adding an additional function that allows us to read in this mesh geometry, extract certain properties from it, which in this case, we're going to use all of the mesh edges, and we're going to adjust our heading or our velocity based on the edges. So we're going to try and align our velocity to the edges of the mesh. So what do we do first? Well, we know that we're going to create a new function, and that function is going to allow us to align to mesh edges. So we can just put this above our snap to mesh, and we can call this align mesh edges. So align to mesh edges, but I'll just shorten that to align mesh edges. You could shorten it to mesh edges or seek mesh edges, but we're actually aligning, and what are we using? Mesh edges. So that's why I'm calling it that. What do we need to input here? We need to input first self, and then I'll just say pass. Now, the output from closest point is both a point and an index. What is this index? It's actually the face index that closest point occurs on. So that point might be in the middle of a face, but it gives us the face that we're snapping to. So we have a point then drawn on the surface of the mesh somewhere on that face. If we want to snap specifically or steer relative to the topology of the mesh, we could just snap to a vertex closest by, but that's going to be a little bit slower to iterate through all of the vertices on a mesh. Another way to think about it is we could take that face, so take just one face, so represented by the polyline here. If we explode this polyline, we get 4 segments. And we could say, which of these segments, which of these headings, which of these edges is closest to my current one? And then we'll use some factor to align to that heading. So take our heading that is defined by our agent motion and align relative to the mesh topology edges. So what do we need in our align mesh edges function? Well, we need to find the closest face, which we're actually getting the index of in our snap to mesh. So we'll be able to use that index to search through all of the faces on the mesh. And then we need from that face all of the vertices on the face. So the first thing we need are all of the vertices, which I'm going to say m underscore vertices equals rs dot mesh vertices. We need to input a mesh ID, so an object ID. And then what else do we need? We need mesh, and we're going to call this T faces. And we're going to use mesh. Actually, we'll call this face vertices rs.mesh face vertices. So what does mesh face vertices take in and what does it give out? So it takes in an object ID, so that's mesh ID, okay? What does it return? It returns the vertex indices of all faces of a mesh object. So vertex indices of all faces. So what is that in type? Index, 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 all inside a tuple, which we can iterate through. So the first thing we need is to get which face in these mesh face vertices, so which of those faces, and then once we've gotten that face, we can use vertices indexes with our mesh vertices list to get each one of our edges. So the first thing we need is one particular face that is the current face closest to our self.pos. How do we do that? Well, we have the face index here in our snap to mesh. So what we need to do is pass that into our align mesh edges. We can do that by calling self.align mesh edges and then feed in that index value. So we'll call that inside of our snap to mesh, feed in that index value as underscore index, and now we can get our face and set that equal to m face underscore vertices of underscore index. So that gives us our one particular face. We can print this face just to make sure that this is working. I'm going to hit play, select our mesh, and then one agent, and we get 4 indexes returned. So each one of those indexes are the indexes of the vertexes that belong to that particular face. So that's working, and now we can go ahead and move on. So what we want to do now is take that face and basically grab from that face all of its vertexes. So we can call these VTX for vertexes and set this equal to, what do we want to set this equal to? We want to set this equal to face 0. So that gives us the first index. And we don't want the index, but we want the actual point there. How can we get the actual point? We can use our vertex list by saying m vertices of face 0. Now we also want m vertices, not of face 0, but of face 1, so the second vertex index. And then we want index 2, so the third vertex index of that face. Now, how do we know whether or not this particular face has 4, 3, or more vertices to each face? Well, we use quad remesh, so it should be all quad meshes. But to make this more robust, in case we don't have a quad mesh, we know that all meshes have to be at least triangular in face, so we need to have at least 3 values. So if I just close that list, we know that we have at least that many vertices to plug into our list. But we could check and see if there's a 4th one. So if, and then we could say if face, if length face greater than 3, so if it's 4, and here we could even say if face length equals 4, so that we know it's exactly 4, and we want to omit all faces that have more vertices than 4. So if length face equals 4, what are we going to do? Vertexes.append. What do we need to append? We need to append our m vertices of face of index 3. So if the length equals 4, then we have a third index there. So fourth item, index 3, and we can append that to our list. So that takes care of whether or not it's a triangular face or a quad face, 3 vertices or 4. Now what do we want to do? Well, we want to collect each edge of our face. So this was get vertices on face. Now we need to collect each edge of our face. We're going to consider each edge as a vector because we know that we want the vector to be able to add to our current vector. So we can just go ahead and say we'll have a series of vecs which are going to equal our edges. So we'll have an empty list there, and we need to loop through for I in range length vertexes. So this is going to loop through, or allow us to loop through, using the index I through our list of vertexes. We now need a starting vertex. We can shorten this even to just st. So st underscore vtx. What does this equal? vtxs of I. What is the end vertex? End vtx equals vtxs. And then just like the cellular automata, we don't just want I plus 1, we want I plus 1 modulus length vtxs, just in case we get to the end and we want to wrap. So now we have a starting and end vertex for each one of our edges. How do we actually make the vector? We can set that vector equal to vec and make it using vector create, which takes in a to point and a from point. So what is our to point? End vtx. What is our from point? Start vtx. And that's all. So we've now created each one of these, but we don't want all of these vecs. And in fact, we don't even need this list, because all we care about here is which one of these vecs is closest to our current vector, so our current heading. How can we do that? Well, we can say our closest vec, which we'll just say is clst underscore vec, our closest vec. We can start off with a none value. And then what about our closest angle? Closest angle we can set equal to just a very high value. And now how do we use these values? Well, as we loop through, we can check the angle with vector angle. And what angle are we checking? We're checking the angle of the edge vector that we're currently looping through and our current one. How do we determine which one is closest? Well, we're going to determine which angle is the lowest. So if angle is less than our closest angle value, which right now starts with a really high number, but as we iterate through, only if angle is lower than the previous one will it be stored as our closest angle. So closest angle equals that angle, and closest vec equals that vec. So this is one way that we can get the closest value, or in this case the closest vector, to our current heading. And now what do we have to do at the end here? We need to update our self.vec to be averaged, so plus closest vec, to be averaged with our closest vector. So added to and then divided by 2. We can also update this and make this a weighted summation or a weighted average, but we'll just go ahead and start with it as an even average, and then we can come back to it and make any adjustments. So that should be all, and now we can click play and run. So we're missing a parentheses to close out that line 37. I think that should be it, so I'll click play now and let's try and run it. And now I'll select all of our agents. Okay, so we're not getting any errors, but we're only getting one small curve drawn out. Why are we getting one small curve? Well, this is because we've limited all the way at the bottom our range down to 1. So we can increase this now back up to 100, click play, select our mesh, and then select all of our agents, hitting enter, and we now have our agents drawn out. And you can see here our agent motion now is actually following this edge all the way down. So they're much more precisely tracing the edges. And you can actually see here where we don't have an agent that's getting influenced by our other agents, we actually get them following even more directly the edges of our mesh. If we wanted to turn down that influence slightly or turn up, either one, we can try both, then all we have to do is adjust a multiplier applied to each one of these two values. So we could say 2 times self.vec and 0.5 times our closest vec. So this is going to influence more towards the agent motion than our actual mesh topologies. So now if we click play, select our mesh, select all of these, we see them actually following the agent motion more than the direction from our mesh. And we could do this, and we could continue this on using 3, and then here we could use a value of 1/3 times our closest vec. Hit play, select our mesh, select our agents. And if we wanted to turn it up, we could just flip these and use a value here of 1/3 for our self.vec plus 3 times our closest vec. Hit play, select our mesh, select our agents, and we now get them aligning to our mesh edges a lot more. If we turn off our agent rules here, so we just turn these briefly to 0, and then leave notes 0.6, 0.2, 0.8 is what they were, and then hit play, select our mesh, select our points. We just get our agents tracing the topology edges of our mesh. If we now slowly turn on each one of these, we'll get those trails being affected by our agent rules. So we can try turning. Let's start with just cohesion actually. So cohesion, let's go really high, so 2.8. So the cohesion now, even though we have still our snapping and aligning set in favor of our closest edge length, we're still able to get that cohesion to overwrite it by making that value really high. If we go down to 1.2, hit play, select all of our agents, we can see them cohering but then aligning with those edges. If we make this 3.0, then that alignment now should cancel out this weighting, so we should get them evenly weighted. If I hit play, select our mesh and then our points. So our alignment is both agent alignment as well as the mesh edge alignment. And now if I turn up cohesion slightly, hit play, select our mesh, and then our points. We now get convergence of our agents, and then they run along the surface of the mesh. We could make that 2.0, separation of 0.1, and coherence or cohesion of 0.8. Hit play, select our mesh, select our points. So it's still looking a little bit sloppy, but I think that's because we just have misalignment a little bit between some of these parameters. So we could go ahead and continue just fine-tuning them. Maybe we want actually a higher cohesion value, and we'll take separation out for now. And then our alignment can stay at 2.0. So that gets our agents cohering quickly. I'm going to step that back to 2 and step our alignment to 1. That's looking a little bit healthier, so there is coherence, but it's slower coherence, so it's not so drastic. And then once they cohere, they do follow the edges of the mesh, so you can see that happening there. One other thing that we might do is actually take our vector that we're using from the closest vec, and we might scale that or ensure that that is based on our values up here. So let's default to a length of 1 by using vector unitize, inputting a vector, and set that equal to itself. So we're going to unitize that vector to ensure that the vector length is 1. Now it looks like our edge length is pretty close. Yeah, it's 1.8. So this will actually scale down that influence slightly so that we have kind of slower acceleration still, while still keeping this variably weighted. So if I click play now, select our mesh and then our points, you can see that that's a little bit slower. And you can tell the speed because it's actually depositing more points along that mesh, or in a tighter bunch along the mesh. Also, if we wanted to limit our acceleration or limit our velocity, we could add up at the top here, along with radius, a max vel. We could set this equal to 0.2. We could take that max vel then, bring it all the way to where we are updating our vel, which is going to be here. So our final update is going to be align mesh edges. We could also, though, do it after we update our snap to mesh. So we could just say self.vec equals rs.vector scale. What do we want to scale? We want to scale a unitized version of self.vec. What is the scale? The scale is our max vel. So this just applies a multiplier to limit our velocity so it doesn't get too crazy, and this would allow us to kind of snap more finely to the surface of the mesh. So we can actually move this, instead of doing it after, we want to move this before we update our position, and actually before we put it in there as well. So we want to do it right before we update our position here. And then when we go into snap to mesh, we can now, instead of using a 1/3 factor here and a 3 factor there, we can just average them directly. And here where we're unitizing this, we can also scale, vector scale, and we can use our max vel. So max_vel. So that's going to scale our closest vector as well based on that max vel. And now if we click play, select our mesh and then all of our agents, we can see those points being deposited based on that max velocity. So it's a lot closer snapping to the surface of our mesh. If we increase that value, then we'll get a further spread for each of the distances between each point on our agent trails. So you can see several of the agents are aligning here, cohering and then aligning and following those edges all the way across. And if we wanted to weight this edge vector either higher or lower, then we could do that as a multiple or a factor of our maximum velocity. So we could say ×2 there, hit play, select our mesh, select our agents. So we get them kind of coming off of the edges more, or we could do divided by 2, select our mesh, select our agents, Then we could also turn down our cohesion. And now we have those agents running on the surface of our mesh with their complex behavioral rules. So that's all for this introduction to 3D agents, as well as the second part, which is the conversion into a mesh crawler, taking those 3D agent-based rules, adding an alignment to the mesh edges, and also snapping each one of the positions of each agent to the surface of the mesh. We could do this same exact thing. Instead of with mesh edges, we could do it with certain UV data or parameters from a surface. We could also snap very easily to the closest point on a surface instead of a mesh. So if you wanted to do it directly onto a poly surface, I'll leave that up to you all to experiment with. How could you do that on a poly surface? It's going to be pretty much the same structure, but if we want to use the align mesh edges, we'll have to rethink a little bit how to structure that, since poly surfaces have edges, but they're not as dense and they don't exist kind of on their surfaces. Now what they do have are U and V's. So they do have U and V parameters. So we would have to process them in a way that we could use those U and V parameters to follow along the U and V parameters, or the U or the V. So we could even bias it in that particular example. Okay, so that's all for this video. In the next one, we're going to cover an algorithm called gradient descent. Now, gradient descent is applicable for a wide range of things. However, we're just going to be looking at a geometric example of a gradient descent on a surface. So we're going to look at a surface and basically a kind of water flow where the particles on the surface seek out the lowest point on the surface and slowly navigate towards it. So that'll be the next video on gradient descent, which is a kind of similar structure here, but it's another way of interfacing with surface or mesh geometry with kind of motion-based particles or trails on their surface.